Fred, that does it for today. Now we can go over the new isolated field alternator and electronic voltage regulator. That is, if you're still interested.
I sure am, Mike. The alternator I understand, but that little black regulator box is something else.
Okay, but before we get started on the new system, remember that it's alternators, plural. There are now 3 different types of Chrysler-built alternators in use. They all fit the same mounting brackets, but you can't interchange them because they're different electrically. You see, the familiar grounded brush alternator with an electromechanical voltage regulator was the first type used on Chrysler Corporation cars. As you know, this alternator has one brush connected to the single field terminal. The other is grounded to the alternator housing. Next comes the insulated brush type alternator used on the 69 Imperials and some special applications. Here, both field brushes are insulated from the alternator housing. One brush connects to the single field terminal, but unlike the earlier type, the other brush connects to the rectifier heat sink instead of ground. Now, that brings us to the new isolated field type alternator used in all of our 1970 models. This alternator also has both field brushes insulated, but each brush has a separate field terminal. Since neither brush has a direct ground or heat sink connection, the internal field circuit is completely isolated. Now, as you might expect, the voltage regulators and wiring used with these alternators also have electrical differences. Now, this means that each type of passenger car alternator must be used with its matching type of voltage regulator.
Don't forget the exception, Mike.
Oh, hi, Tech. Thanks for the reminder. Tech is referring to the alternators used on some Dodge light-duty trucks made late in '69. These are isolated field alternators which are modified to use the electromechanical voltage regulator. In this case, the horizontal field brush is grounded to the alternator housing by a permanent jumper wire. If you replace one of these isolated field alternators, use another of the same type and be sure to install the ground jumper wire. Now, returning to voltage regulators, the electronic voltage regulator for the insulated brush type alternator provides the ground for the field circuit. This regulator has a 3-prong connector with terminals for ignition, suppressor, and field leads. The electronic voltage regulator for the isolated field type alternator also provides the ground for the field circuit. In this system, the regulator has a 2-prong connector with terminals for the ignition and field leads.
Now let's see if I've got that all straight. We've got a grounded brush alternator with an electromechanical voltage regulator, an insulated brush alternator with a 3-prong electronic regulator, and an isolated field alternator with a 2-prong electronic voltage regulator.
Absolutely correct, Fred. And take it from me, the new charging system is a real winner across the board. Car owners get better electrical system performance, and you master technicians get a system that's easier to service. Mike, what goes on inside the electronic voltage regulator?
Well, operation of the 2- and 3-prong regulators is basically the same, even though their external field circuit wiring is slightly different. There are no moving parts or adjustments, so we service these regulators by replacement. Now, as for regulator operation, the heart of our electronic voltage regulator is a solid-state device called a Zener diode. This special type diode conducts current only when the electrical system line voltage rises above a certain level. In other words, a Zener diode is a voltage-operated electronic on-off switch. Here's how it works. When line voltage drops below the specified level, the Zener diode shuts off the current which controls the field circuit transistors 1 and 2. This permits the field current flow needed for increased charging output. Zener diode switching action is continuous and very rapid to regulate charging voltage accurately. Now, when system line voltage increases to the Zener turn-on level, the diode conducts current. This controlled current turns on transistor 1, which then turns off transistor 2, blocking the direct flow of field current. When transistor 2 turns off, the field current then passes through the field suppressor diode, which limits the current flow to reduce alternator output.
I get it. The transistors control the field current, and the Zener diode controls the transistors. That's simple enough.
Well, there are other parts in the regulator which compensate for temperature change and other variables, but we've covered the main points of regulator operation. So let's talk about troubleshooting and testing.
Hey, they've made some changes in the charging system, service diagnosis section of the manual.
Yep, when you read the manual, you learn things. The clues listed in that section really help you zero in on trouble causes in a hurry. Another way to save time is to use the new electronic voltage regulator tester. In fact, this new tester is so easy to use that I check the voltage regulator first on practically every charging system job I do. The tester operates on house current, so you don't need alternator output for checking. And you can check the 2- and 3-prong regulators on or off the car.
Mike, you're due for a breather. So take a break, and I'll tell Fred how to use our new handy-dandy voltage regulator tester. It's simple to connect and operate, but always remember that the ground lead must be connected before you push any test buttons, or you may damage the tester. First, make sure the selector knob is in the regulator test position. Next, you connect the ground lead to the regulator housing or a good body ground and plug in the power cord. Then remove the wiring harness connector from the regulator and plug the test connector into the regulator socket. With the selector knob at regulator test position, press the test button in. If the regulator is okay, the pointer should be in the green or blue range when regulator temperature is below 80 degrees, and in the green or yellow range above 80 degrees. Then, as you hold the test button down and push in the black A button, the pointer should stay in the correct color area on the dial. Then release the A button so you can make the final regulator test. Keep the test button down and push in the red B button. The pointer should now read above the red line on the dial. When you finish testing, remove the test connector and power cord plugs, but leave the ground clip in place so you can use the tester as a voltmeter. If the regulator checks okay on a car that's in for no charge trouble, use the tester prod to check for voltage at the regulator wiring connector terminals. Move the selector knob to the 18-volt position and turn on the car ignition switch for the test. No voltage at the terminals usually means an open in the field circuit or alternator rotor.
Thank you, Tech. Now, on a no-charge job where the voltage regulator passes the test and the field supply voltage is okay, the alternator internal field and the charging circuit are next in line for testing. However, before you make any additional tests, give the charging system a quick visual inspection. Check for obvious things like alternator drive belt condition and tension. A glazed or worn belt can slip and reduce output, even if properly adjusted. And don't forget that over-tightening the belt can ruin the alternator bearings. And it's easy to eliminate the possibility of high resistance at the battery connections by cleaning up the cable clamps and battery posts. Resistance here can make the whole electrical system act up. So don't be fooled by a clean-looking cable clamp that may actually hide a layer of high-resistance lead oxide. After the regulator and wiring tests, the alternator internal field circuit is the easiest item to check next. Loosen the drive belt temporarily so you can turn the rotor. Then, disconnect the green field lead which comes from the voltage regulator. On trucks, the color of this lead varies with different models, so check the diagrams to get the right one. Next, connect the test ammeter between the alternator field lead and its terminal so you can check the internal field current draw. Switch on the ignition to supply field current and slowly turn the pulley by hand as you watch the test ammeter indication. Current draw from 2.3 to 2.7 amps is okay. A low reading points to high rotor coil resistance or poor brush and slip ring condition. A high reading usually means a short or a ground. No reading, and open in the rotor or field lead. If the rotor checks out okay, the next test point is at the alternator output terminal. This terminal is normally hot when the battery is connected, so you can check it for voltage without running the engine. No voltage at the terminal tells you that the charging circuit is open somewhere between the alternator and the battery.
Hold it right there, Mike. It's time to turn the record. So if someone will oblige, we'll move on with our story.
Okay, Fred. If you get a voltage reading at the alternator output terminal, it means that you can check the charging circuit resistance and current output. To begin, you first disconnect the battery ground cable, and then the alternator output lead. Move the ammeter connections from the field test to the alternator output terminal and its lead. When the ammeter is connected, reconnect the battery ground cable. Leave the green voltage regulator field lead off and connect a jumper between the alternator field terminal and a good ground. On isolated field alternators, the other field lead remains connected for all tests. With the ammeter and field ground jumper connected, we then connect a test voltmeter. The positive lead goes to the alternator output lead, and the negative to the positive battery post. You need manual output control to get an accurate voltage drop indication, so we connect a variable carbon pile across the battery posts. Be sure to turn the carbon pile to off position before you connect it.
We do the resistance test to track down circuit trouble, right?
That's the main idea, Fred. You see, high circuit resistance will reduce the charging current and make current output tests inaccurate, so we make the resistance test first. Now, to check the circuit resistance, start the engine and hold it at curb idle speed until you're ready to take a reading. You see, with a field terminal grounded, charging current can quickly climb high enough to cause damage even at fairly low engine speeds. For the resistance test, you adjust the engine speed and carbon pile slowly to get 20 amps on the meter. At this point, the voltage drop reading should not be over 7/10 if the charging circuit resistance is within limits. To locate high resistance in the circuit, keep the output at 20 amps and shift the positive voltmeter clip to each connection in the charging circuit. You'll find the resistance between the connection, which shows the high voltage drop, and the point where it disappears.
Sometimes you can find the high resistance without moving the voltmeter lead, if you wiggle the wires and connections while you watch the meter for pointer movement. And don't forget the body ground connection. That's important too.
Good points, Tech. For the current output test, drop engine speed to curb idle and back off the carbon pile. Then move the positive voltmeter lead to the alternator output terminal and connect the negative lead to a good body ground. The output test is made at a specified speed, so we'll also need a tachometer. Once again, you adjust engine speed and the carbon pile slowly to guard against high output damage. When engine speed is at 1250 and the voltmeter reads 15, the ammeter reading must be within the limits given in the service manual. Low output here points to trouble in the alternator. And that brings us to the charging voltage test.
Before you do any testing, make sure the voltage regulator mounting screws are tight and the housing has a good ground. Some technicians forget that the ground side of the circuit is just as important as regulator wiring and connectors. Also, the battery charge level must be at least 1200 to get a prompt charging voltage test. If the gravity level is below this point, recharge or substitute a charged battery for the test.
Thank you, Tech. For the charging voltage test, we reconnect all the alternator leads and make sure that the regulator wiring connector is plugged in and secure. Then, connect the test voltmeter positive lead to the ignition ballast resistor at the end with 1 or 2 blue wires. The negative meter lead goes to a good body ground. To make the test, run the engine at 1250 with all lights and accessories turned off. We've already checked the regulator, so if the reading is now slightly above specs or fluctuates, we've got high resistance in the field circuit.
I'm sure everyone will agree that the new electronic voltage regulator tester is a real time saver. But if your tester is out of service for any reason, you can follow the regular alternator and regulator testing sequence given in your service manual. Mike, while you're at it, how about covering bench tests for the new alternators?
I figured that was coming. Well, in general, it's common practice to make all the bench tests on each job, but you can pinpoint trouble causes if you watch for clues when you make the tests on the car. For example, if the current output test reading is 5 to 7 amps lower than specified, you can suspect an open rectifier as a possible cause. Much lower output can point to a shorted rectifier. Now, we've already covered the possible results of the field coil current draw test, so let's go on to the field ground test. We check the alternator internal field circuit for ground with a 110-volt test lamp. First, put the alternator on an insulated surface. Then, touch one test prod to a field brush terminal, the other to the end housing. If the test lamp lights, the rotor or brushes are grounded. To locate the ground, first remove the brush holders and the end housing. Then, clip one test lead to the remaining end housing and touch the test prod to either slip ring. If the lamp still lights, it means that the brushes are okay, but the rotor is grounded.
Make sure a nylon washer is under the head of each brush holder attaching screw, or you'll get a direct ground to the end housing. This is a special size screw, so don't try any substitutes. And now back to you, Mike.
Okay, Tech. When the alternator is apart, you can get at the rectifiers for checking. I always use the rectifier tester because that way you can leave the rectifiers connected. If you don't have a tester, you can use the battery and test lamp method given in the service manual. To use the rectifier tester, put the stator and end housing on an insulated surface and plug in the tester line cord. Connect the clip lead to the alternator output terminal for checking positive rectifiers. You move the clip lead to the end housing for negative rectifiers. To make the test, first touch the tester prod to the connector lead of each positive rectifier in the heat sink and note the individual readings. Then, move the clip lead to the end housing and use the prod on each negative rectifier. The reading for a good rectifier should be okay, or 1 3/4 amps or more, and about equal in each group. A shorted rectifier reads near zero and causes the remaining good ones to read low. An open rectifier shows about 1 amp, with the others in the acceptable range. If you find open rectifiers, be sure to inspect the stator windings for burnt areas or signs of overheating. This overheating usually results from a short-circuited stator winding, which also overloads the rectifiers. A faulty alternator capacitor can also cause open rectifiers, so be sure to disconnect the capacitor and test it for being open or shorted. And as you know, rectifiers can also be blown if the battery is connected backward, reversing the polarity. And one final point. If the rectifier tests are borderline or doubtful in any way, insulate the stator frame from the end housing and rerun the tests. If the rectifiers now test okay, check for grounded stator coils.
Okay, Mike, we've checked the internal field circuit and the condition of the positive and negative rectifiers. That leaves the stator windings, right?
Correct. And to check the windings, you have to disconnect the stator leads from the rectifiers.
When you unsolder stator leads, don't blast the melted solder off with air, because you might blow fine particles on the other rectifiers and short them out.
Good points, Tech. Now, with the stator leads disconnected, remove the stator from the end housing and check it for grounds. With the stator on an insulated surface, clip one lead of the 110 test lamp to the stator frame and connect the other to any stator lead end. If you get a light, one or all of the windings are grounded. Finally, we wrap up our bench tests by checking stator windings for continuity. All you do is connect one test lead to one stator lead and touch the other to both remaining leads in turn. The test lamp should light if the windings are okay. No light at either or both leads means an open winding. In either case, if you find the stator grounded or open, you'll have to install a new assembly. If the stator checks okay, or you're installing a new part, carefully resolder the stator leads at the rectifier ends, and the job is done.
And on the subject of soldering rectifier leads, don't ever let me catch anyone using acid core solder or soldering paste, because that's the surest way to get corrosion started. Well, fellas, that covers the highlights of servicing our new alternators, from identification to the innards of the little black box. Of course, there are mechanical details that are not covered here, but you'll find it all in your service manuals. Be sure to study and save your reference books for this session, so you'll have the testing procedures handy when you need them. And it won't hurt a bit to give the service manual some extra attention. See you all at the next meeting.